So next we're going to look at calculating conditional probability. And this one's pretty simple. It's kind of taking a closer look at this, the probability of 60 plus minutes given public transportation. This given public transportation portion means we're only looking at public transportation. So we're only looking at the row that talks about public transportation. So the total, so this is basically your probability here. This is the numerator, this is the denominator. So it's going to be out of 329. So little squiggles here. So the 60 minutes or more is right here. So it's going to be 108 out of 329. And this probably reduces, maybe. Let's see. These look like they both divide. No, maybe, I don't know. Let's see. Get out of this. Okay. Let's just see what it says. I put 108, 329. So yeah. So that one didn't reduce. Sometimes it might reduce though. Okay. So let's see what so there's this one. It looks a little bit different. Now this one, I'm actually going to create a table like I've done in the past. So just for visualization, so we can see. It's going to be a 3x3 grid. 3 rows and 3 columns. And then the probability for men, I'm just going to put M for men. Oops, I made it too high. I'm going to clear everything. Okay, so M for men. And then NM for not men. And then here's the total. And then on the side here, I'm going to do botanical sense. And then not botanical sense. Okay, so for the men, probability of these deodorants being for men is 0.55, 55%. Probability of it being a botanical sense for total is 0.18, 18%. And then for it to be both men and botanical, so right here is 0.05, so 5%. For it to be both botanical and for men. And then the total is always 1. So what it's asking for is the probability of 4 men given it's botanical. So here's 4 men given it's botanical. So this is the botanical total. So it's going to be 0.18 is the denominator out of, because it's given that it's botanical, and then the out of the botanicals, the 4 men is 0.05. So this ratio, 5 out of 18, this is it. Okay. It might be difficult to realize this is the numerator, but it helps if you see this. So the given is the botanical, so we're only looking at this column here. That's the total of this column, or sorry, this row. We'll look at this row here, and this is the total of that row. And then 4 men is this out of this row. So that'll be the answer. And this, kind of the same deal. A burger given fries. So fries is this right here. So we're only looking at this. So this is 50% total. 4 plus this 40 in the middle, plus this 10% is 50%. And then of the burger that's part of the fries, we're only looking at this 40%. So 40% out of 50%, or 4/5. Okay, so that's kind of hard for a lot of people to follow, but this part right here where it says given fries means we're only looking at this portion right here. We don't care about anything else. And so the fries is 50%, so that's like 0.5. And then the part that's also burgers, the burgers that are also fries, is 40%. So it's 40% out of 50%, 4/5. Okay. This one too, just to get it done. So female, we're only looking at that column. So it's out of 48. And then invisibility is 32. Now this one does reduce. They both divide by 4. And you get 8/12, and then it reduces further. Both divide by 4 again. So these guys divide by 8 by, yeah. And then, so 2/3. If I did that correctly. Yeah. All right. So on to the last one, dependent and independent events. This one, you kind of follow it along as well. And so it can be tricky as well. So it's really important to read and then think about what that means in terms of probability. So this one, the probability of A is the probability that the first flip is heads. So they give you a nice little diagram here. So the first flip heads meaning there's an H in the first position. And so I already know, just based on a coin flip, the first one's going to be, has a half of a chance of being heads. So it's 1/2. The second flip being tails is also 1/2. The first flip doesn't affect the outcome of the second flip. So if you imagine flipping multiple coins, if you flipped a coin once, it coming up heads or tails does not affect the next flip. So what is the probability of A and B? The probability the first flip is heads and the second flip is tails. You just multiply these together, so it'd be 1/4. But you can see that down here. So if we look at, we're heads and tails, so let's see. I'm going to circle them. Man. Okay, so heads and tails right here. So the first one's a head, second one flips a tails. Head, tails. Head, tails. Should be one more here. Head, tails. So those are all the head, tails. And that's out of 16. So 4 out of 16 is 1/4. It says, are these independent events? Yes, they are, because flipping a head the first time does not affect flipping a tail the second time. So this is going to be similar. This one does not have a table. So it's probably worth it to build one. Or we'll just think about it, okay? So I think I'm going to go ahead and build a table just because it'll keep things cleaner. So here's my table. And we're going to be a 3x3 table. This will just keep your things organized. So the probability that a student plays soccer, so I'm going to put S for plays soccer, and then plays basketball, put B for plays basketball. Notice how I'm putting them on one's columns and one's rows. And then not soccer and not basketball. So this is kind of on or off. These are kind of on or off, so we call them Boolean, true or false statements. So if you notice, if you play soccer, you could also not play soccer. If you play basketball, you can also not play basketball. So that's why there's this column set up. And these are just total, the last column and row are just total columns and rows. Okay. So what is the probability they play soccer? There are 150 students. There are 45 in the soccer team. So I'm just going to kind of put the raw numbers. I'm not going to do percentages on my table. So there's 150 students total, and 45 are on the soccer team. So the soccer team is this right here. So 45 are total. And then 35 are on the basketball team. So the basketball team is this top first row. So 35 are on the basketball team. Out of these students, there are 20 who play both. So here's plays both right in the center right here. So these are 20. So now we have enough information to fill out the rest of the table. So the people that play basketball and not soccer, that has to add up to 35. So it has to be 15 here. And this has to be 25. They play soccer but not basketball. Okay. And then to add up to 150, this has to be a big number because it has to be 105. So there's 105 that do not play soccer. And this has to be a pretty big number too. So there is a, let's see, 100 and, what can I think? 15. 115 that do not play basketball. Okay. And then to play neither. So to add up to 115 has to be 90. So there's 90 that plays neither out of 150. So this should be enough to sort of get us through this task here. So let's see, what is the probability of a student plays soccer? So a student plays soccer is 45 out of 150. These both divide by 5, and so we get 9 out of 30. Wait, am I doing that right? 9 out of 30? Yeah, these divide further though. You divide by 3, and you get 3/10. These both divide by 15. Is that right? I'm gonna do it. 3 and yeah. My brain's not working right now, so I'm a little concerned. So I'm gonna redo it. So this is by 5 get 9. Yeah, I think I did that right. Okay. So I'll put 3/10 in. Or 30%. It's because it's 30%. And then what is the probability that a student plays basketball? So basketball is 35 out of 150. So again, I'll divide by 5 first, and I get 7 out of 30. And that looks like it's going to stay that way. And then A and B. What's the probability the student plays soccer and basketball? So that's 20 out of 150. So divide by 5, we get 4 out of 30, but that reduces further to 2 out of 15. So this is one calculation, another, and then my third calculation's here. So that was 20 out of 150. So divide both by 5. Well, I'm dividing both by 10, really. Yeah, that makes sense. Yeah, my brain. Okay. And then what is the probability of A given B? So the conditional probability that a student plays soccer given that he or she plays basketball. So we're only looking at the basketball column. If it's given that he or she plays basketball, we're only looking at the basketball column. And then it's the probability of soccer out of the basketball column. So that's going to be 20 out of 35. So these both divide by 5. You get 4/7. Okay. So this is all well and good. This is kind of like what we've been doing before a little bit, and then it gets a little tricky. This is kind of more complicated, talking about, you know, what am I trying to say? This is we're trying to, now they're asking if they're independent events. Okay, so you're gonna have to pick two things, generally speaking, because they're opposites. So this is saying that yes, these are equal, or no, they're not equal. Yes, they're independent events, and no, they're not independent. So this is kind of useful because it's showing you with the math how to determine if something's independent or not. And I'll explain what that means in a second. So let's just look to see, this one's easier to determine. So let's just look to see if this is true. Is the probability of A given B, which is what we solved here, right? A given B, that's the same as probability of A. So A given B is 4/7, if I did my math correctly. And probability of A by itself is 3/10. So see how they're not equal? So they're not equal. 4/7 is not the same thing as 3/10. So this is kind of like a word trick, right? So what's the probability of A? The probability of A is a student plays soccer. And so if we know they also play basketball, does that change the probability? So in other words, does knowing that they play basketball change the likelihood that they play soccer? And the answer is yes. And the reason the answer is yes is because the probability is not the same. If the probability that they play soccer is the same whether or not they play basketball, that means basketball does not affect the probability they play soccer. But because they're not the same, the probability they play basketball does affect whether they play soccer. So that means they're not independent events. In other words, let's go back to the coin flip real quick. If I said, you know, flipping the first one tails and the second one heads, does the first one affect the second one? In other words, does it matter that I flip tails the first or not? And they're independent events because it doesn't matter. It doesn't matter if you flip tails or heads the first time. The second time, you have the same probability of flipping heads or tails. In this case, knowing that a student plays basketball, in other words, knowing that heads flip second, changes the likelihood that we can expect for the first one. So that means they're not independent. One affects the other. And that can be seen because the given condition that B has happened changes the outcome.